One very typical example system that beginners of quantum mechanics have to work with is the one-dimensional particle in the box. This does at first glance not feel very physical, but already from this toy system some things can be learned. Primarily it is chosen because the calculations and expressions are comparably simple. We'll get to more realistic systems eventually. Assume that a certain particle can only exist on a section of length L of a line. We can simulate this by saying that the potential energy of the particle would be infinite if it was outside of the segment, and 0 if it is inside. The total energy of the particle on the segment is then only given by its kinetic energy. To work with the Schrodinger equation introduced in the last video, we'll have to find a Hamiltonian, specifically an operator that can extract the kinetic energy from a wave function. As it turns out, it is given by minus h bar squared divided by 2m times the second spatial derivative, where m is the mass of the particle. It is not necessary that you understand where this expression comes from, as long as you believe that it is the one that works in describing nature, but for the more curious, here's a very short quote-unquote derivation. Neuters Theorem tells us that a system that has no spatial dependence will conserve momentum. In a quantum mechanical formulation of the theorem, the derivative with respect to x is the conserved quantity that results from assuming no spatial dependence. So this is apparently the quantum mechanical momentum. Choosing the prefactor minus I(h bar fixes the dimension of the operator. The kinetic energy is given by the momentum squared divided by 2m, which is precisely the expression above. Now we have everything we need. The Schrodinger equation in the allowed line segment reads I(h bar temporal derivative of psi equals minus h bar squared over 2m times the second spatial derivative of psi. This is a partial differential equation begging to be solved. A promising approach is an exponential function for the temporal part and a trigonometric function for the spatial part, and a normalization factor a. Because I script before I record, I already fixed the coefficients such that this function does indeed fulfill the Schrodinger equation and is, accordingly, a valid physical state of the particle. But wait, our solution is only valid on the line segment. Outside of it, the wave function is 0, because we assumed that it is impossible to find the particle there. The Schrodinger equation features a derivative with respect to x, so for it to be defined, psi had better be continuous. At x equals 0, this is already guaranteed by the sign. That's why I picked it instead of cosine. But at x equals L, this is only true for some values of the energy E. Specifically for E equals h bar squared pi squared over 2m L squared times n squared. Because n is a natural number, the allowed values of E are non-continuous or quantized. This is a very counterintuitive result, because we certainly do not see this in everyday life. This is because the value of h bar is so extremely small that these effects only play a role for very small distances L. The more cautious among you might have noticed that the Schrodinger equation features a second derivative, which is currently still not defined, as the first derivative is not continuous. This can be remedied by interpreting the derivatives in the distributional sense, then an infinite potential energy at some point allows for a kink in the wave function. Again, this is nothing you have to understand at this point. This qualitative result is rather general and justifies using this toy system. A spatially confined particle can only take discrete energy values. If you'd like your box to have more than one dimension, not a problem. The expression for the kinetic energy in several dimensions is just the sum over the individual dimensions. The solution to the Schrodinger equation inside the box is then the product of the individual one-dimensional solutions, each with their own quantization criterion. It is worth checking that what I just glossed over is really the case. Are there more solutions than the infinitely many we already found? Find out in the next video. Until then, enjoy life if you can, and don't be ashamed if you can't.